Hello everyone. So this is my second statistical machine learning assignment. Let's go through it. So we have this prostate cancer data set with just 79 patients or people, the sample size, but 500 features with the genes. So right off the bat, we know that we have a lot of features as compared to the sample size. The kappa ratio is 0.158, which is extremely small and smaller than 1. So we have an issue of case of dimensionality where overfitting becomes really easy. And so we went ahead to look at the response variable, the balance in there. We have 37 non-cancer patients and then 42 cancer patients. So definitely there's no class imbalance. Now we needed feature selection, so we just use the Kruskal Wallace to test for the nine most strongest predictors. And these are the nine most strongest predictors. We looked at the above plots, we realized that they show clear separation between the cancer patients and then the non-cancer patients. But when you look at the nine weakest, this is the box plot, you can see there's a lot of overlap going on here. And we also built a classification tree on the data set with CP equals 0.01, where we have four terminal nodes, and you can see the variable at the root, which is the S20 12 90 80, which was actually ranked fourth. If you look at the list here, it was actually ranked fourth by the Kruskal Wireless. Why this? Because the CART or the decision tree uses a different criteria, and that is it looks for the best binary split instead of looking at the overall separation. And so we looked at the correlation plots, which also shows severe multicollinearity. You can see the condition number was very high, so the severe multicollinearity. Yes, and we built different models on this data sets. And then this is the ROC curves on the training data set. You realize that the one n, which is the k is equal to n for the k nearest neighbors, had a perfect AUC of 1, which is actually great. But so what? We are just dealing with the training data sets. And so it's just memorizing everything. This is actually overfitting, right? And then the trees also had AUCs around like 0.85 and 0.9. Now, um the raw test came in when we actually did the holdout validation, the 100 random and the 70-30 splits, and look at the distribution for the test errors. We realized that the KNN was actually beating the trees. Yes, it was winning. And we can see that the tree where the CP is equal to 0, there was no pruning, and so it performed worst. It was overfitting, right? So the takeaway is that complex models aren't always better. I mean, if you have many features and samples, just going for a simple model with a good feature selection. And even though the KNN won numerically, but trees are more interpretable. In this setting, this is like a medical setting. So it's better to explain to a biologist which gene matters than just using the black box like the KNN. Now look at our second question where we looked at KNN as a kernel method. And so a kernel method is just like if 2 points are similar, they should probably have the same label. That's the whole idea. So we show that the KNN is actually a kernel method. This is the formula. We show that this sign it just measures how similar X is to each training point, and the closer point gets the higher weight. And then the alpha I is just picking out the k nearest neighbors, just 1 if XI is a neighbor and 0 if it's not. Now the YI is just the label. So the whole thing is saying that look at the k nearest neighbors, weight them by how close they are, add up the votes, and then the sign will tell us which class wins. So that's how the KNN works. And then we also looked at how this pi dx is estimating the probability that you belong to class one. And it's just asking that among the k neighbors, what proportion are positive? Yes, and if most of your neighbors are positive, the pi dx will be high. If it's negative, it will be low. Now we proved that there are two ways of doing KNN, the voting one and then the probability way. And then that is the exercise 3. They are all the same but different methods. For the hypothesis space, which is y is equal to 0, 1, is because we are the space will be y is equal to 0, 1, because we are using an indicator and that outputs 0 or 1. And we have other methods that act like this kernel. We have the logistic regression, the Nabaraya, Watson, and then the decision tree. They work the same way, but they all estimate a probability and check if it's above 0.5. And they just estimate that probability in different ways, but they are working the same way. So thank you very much.